Hello, my name is Andreas Kesaris, and this is my presentation on my third-year project on augmented reality-based remote control through the Microsoft HoloLens. This project aims to develop a novel AR-based remote control system that can allow the end users to remotely manipulate an object through an augmented reality platform. The controlled object can be an LED on a circuit, and the AR platform can be the Microsoft HoloLens. The most important requirement, though, is to achieve remote control without physically interacting with the hardware and without coming in direct contact with a controlled object. The motivation for this work grew with the exponential advancement of the AR technologies over the last few years. The need to adapt with a highly competitive manufacturing environment like the newly introduced Industry 4.0 and its faster, smarter, and more efficient ways, the launch of the fifth generation of wireless mobile network, and as AR technologies, and especially when it comes to remote control over large distances, the requirement for a fast and capable network is very important. And finally, with the worldwide adoption of AR technologies, especially when it comes with introduction of HoloLens goggles that are an affordable and very useful tool, it has never been a better time for this project. So the project was divided into three main sections and therefore was consisted of three main objectives: the development of an AR platform application, a functioning server, and a controlled object. Starting from the AR application objective, a user interface needs to be developed that can allow the operator of the AR platform to control AR elements using only his hand gestures. That, of course, would be a great advantage, as the user can still be aware of his surroundings while still controlling a device on the other side of the world, perhaps. Finally, those AR elements need to be designed in a way that can trigger commands that can get transformed into packets and are ready to be sent to the project server. As mentioned, the server needs to collect the HoloLens packets, analyze them, possibly handle the simultaneous connection of multiple HoloLenses, and finally forward the packets to the microcontroller. Which leads me to the third and final objective, the controlled object. This will be a microcontroller connected to a physical controlled object that can receive packets from the server and respectively control the device. I mentioned above the term augmented reality platform. To understand how technology like this one works, it is good to view all three of the digital reality technologies and compare them with each other. In this slide, there is a clear demonstration of the differences between those three digital reality platforms. First, the virtual reality, also called VR, which is a completely digital environment. The user wears a headset that encloses him into a synthetic and virtual experience with no sense of the real world. That means that the user can manipulate VR elements, but without any effects on the real world. Then there is the augmented reality and the merged reality. Most of the times, an AR device is also an MR device, as these two terms are very similar with each other since they both are technologies that expand on the user's existing reality and physical world by adding extra layers of digital augmented elements, often with the use of a camera. The only difference is that in the merged reality, the user can interact with those elements. So as mentioned by the title of this project, this is an AR-based remote control system through the HoloLens headset. But the HoloLens goggles are not just an AR device, but instead it's a mix of augmented and merged reality platform. For that reason, when I will be referring to a HoloLens or in an augmented reality feature, I will be actually referring to a mixed reality technology. Moving forward, here are some applications of AR and VR technologies. On the left, an AR application can be seen that allows an engineer to view instructions in a more accessible way, something that makes him more efficient. Then on the right of the slide, there are two examples of VR-based remote control projects. One that uses a VR headset to control a robotic arm, and the other one of a whole NASA space robot that can help in tasking International Space Station and even future space exploration. Similarly, with these ideas, this project will use the mixed reality platform HoloLens and explore its capabilities in the remote control sector with a combination of the 5G network. The inspiration for this project's structure was taken from the tactile internet architecture. More specifically, as shown in this figure, the end-to-end architecture of the tactile internet is divided into 4 stages, and it has 3 key domains: a master domain, a network domain, and a control domain. The master domain is basically the human that operates the human system interface. This is the domain that records the real-time data and creates a request that is targeted towards the control domain. The network domain represents the medium bidirectional communication between the master and control domains, and therefore it kinetically connects the operator to the remote environment and the control object. This is a domain that the features of the 5G network and the tactile internet shine. The control domain is a physical object and that the operator wants to control using specific command signals from the master domain. More information on the actual project structure and architecture will be discussed later. The hardware side of this project is contained inside the master and control domain. As mentioned above, the HoloLens Gen 1 headset will be the AR platform for this remote control system. The HoloLens is a wearable headset that projects a visible image in the user's point of view. It uses specialized optics and transparent visor and holographic processing to render 3D digital images in space that are only visible to the user that is wearing the device. The rest of the real world is preserved, allowing the wearer to manipulate the holograph and perform other tasks at the same time. Then for the control domain, an Arduino board will be used as the object's microcontroller, as it is a low-cost solution that is fairly easy to put into use, but at the same time could perform complex functions and handle complicated projects. Moving to the software tools used in this project now. For the master domain and the HoloLens, a combination of the Unity 3D software, the Mixed Reality Toolkit, and the Visual Studio Code were used to develop the HoloLens user interface application. More specifically, Unity is a cross-platform game engine with an integrated development environment (IDE) that is used to develop and program games, animation sequences, and apps for many platforms. In order to program an application for an AR platform though, the Mixed Reality Toolkit was required. MRTK is a toolkit for building mixed reality experiences for HoloLens and other platforms. It contains AR objects, physics modifications, cursors, and overall useful app development utilities. For the network domain, the server was developed on the Visual Studio Code environment, and the clients were simulated using the Backend Center. This tool allows the user to generate and send TCP and UDP messages to specify destination. Finally, for the control domain, some code was written on the Arduino IDE that processes it, debugs it, compiles it, and uploads it to the board. The detailed project structure is shown in this figure. Here, in the master domain, the hand gestures done by the users are recorded by the HoloLens cameras, get analyzed by the application developed using Unity 3D, and depending on the interaction of the application, a packet gets sent through the network domain to a server that then forwards them as a request to the control domain, and then the Arduino microcontroller controls the object. The following slides will discuss the methodology and results from each of the mentioned domains. So let's start with the control domain. The aim of this part of the project is to find a microcontroller that can connect to the internet and then be able to receive information to trigger events. After some research, it was decided that the Arduino Maker Wi-Fi 1010 is the perfect fit for this project, as it can support both analog and digital readings, has a compact design, and can connect to the internet either through the Wi-Fi shield that is already on the board or by using an external Ethernet shield that connects straight to the board and allows wired connection. The development of this domain started with the connection of the Arduino board to the internet using the Wi-Fi shield to connect to a 4G mobile network. Then a script was written on the Arduino IDE that opens up a port and waits for TCP packets to arrive from the project's Python server. Finally, the script would read the packets, and depending on the message, it would switch on or off the correct LED. Next is the master domain. The process in this domain begins with the operator wearing the HoloLens headset and launching the project application that is already installed in it. The user can then interact with any of the AR elements using the AirTap gesture, which triggers the HoloLens TCP client script that generates a TCP packet with the control command requested by the user and sends it to the server. And now for the HoloLens app development. The Unity game engine was utilized as the core development platform for this application. Unity manages the linking and integration of component assets that are used within an application project. These assets may include 3D objects, text data, C#, scripts, images, audio, and others. In addition, Unity provides its own built-in 3D and 2D components. To make an application functional on a HoloLens though, one must import the mixed reality toolkit utilities. As mentioned before, the toolkit includes many useful modules and assets like cursors, gesture simulations, gaze modes, and many other tools that transform any 3D application into an interactable HoloLens application. During the app development, several custom C# scripts were also developed using the Visual Studio Editor to add custom features like the changing colors of the buttons and the TCP client functionality. These figures give an idea of what the user interface looks like in the application. More details on the project application will be shown in the demonstration part of the presentation. So, this concludes the master domain development, and we can now move to the network domain. The structure of the server is as follows. The server initiates when the Python script starts running. The first thing the server does is to open the socket number 1 and start listening for new clients, or in other words, HoloLens users. Once there is a client that wants to send a package to the server receives the message, decrypts it, and can possibly even store it. It is at this point the server opens up a second socket for the server and the Arduino connection, and forwards the packets to the Arduino board. Once this process is complete, both connections get toned down. This process is able to occur with multiple clients in parallel, as an algorithm ensures that the simultaneous communication of multiple clients works smoothly and seamlessly. When designing the TCP server, there were two key requirements that were considered: the communication reliability that can be provided by a protocol with good error checking mechanisms, and the low latency that is only possible with a network environment that provides high-speed communications no matter the number of clients, the number of packets, and the geographical distances between server and client. As mentioned before, the networking protocol used in this project is a TCP. The decision was only made, however, after the comparison with another broadly used protocol, the UDP, showed that the TCP is one of the most reliable protocols. More specifically, in the table on the left, a list of pros and cons of each protocol is listed. TCP is a connection-oriented protocol, and its packets make their way across the internet from one computer to another, something that guarantees a safe delivery of the data to the desired destination. It also does extensive error checking, something that makes it even more reliable, but at the same time makes it heavier and a bit slower. On the other hand, the UDP is a connectionless protocol, something that makes it lightweight and therefore faster, but it doesn't check for errors, and so the delivery of data to the destination cannot be guaranteed. This data can also be demonstrated graphically, as on the right of the slide we can see that the UDP has a larger throughput than TCP, but also has a bigger error rate. The project needs a network solution that can deliver an organized, error-free, and low-latency remote control solution. As seen above, TCP can provide an organized communication as it controls the flow of packets sent, and therefore the amount of packet collision is minimized. At the same time, the same flow controls that make TCP more reliable are very slow when it comes to recovering the missing data quickly enough to be useful in real-time communications. Even though the data integrity is very important for the project, it also needs to be balanced with high-speed connections to ensure that the fast-paced communication can remain uninterrupted. That's where the 5G technology comes to play. The following is an analysis that compares the latency differences between a 4G and a 5G network. Results collected from this project were used in this analysis. More specifically, the packet's latencies of up to Three different clients at the same time were used, and the rest of the data were calculated respectively. Then the 5G data were created with the assumption that the 5G latency will be 10 times better than the 4G network. The graph on the right, it is then evidence that the 5G technology has less round-trip time latencies than the 4G technology, as it can handle multiple users at the same time without sacrificing the connection speed. The 5G analysis for this project continued with two more factors that could potentially increase the latency. First, there was a need to check the network response to clients sending multiple packets each. This would be useful, as in the case of the controlled object being more complex, it could require multiple packets from each user in order to control it. It is clear again, looking at the graph on the right, that the 5G latency stays at a low value even with a large number of packets in the network, whereas the 4G round-trip times could reach, at the worst-case scenario, up to 80 milliseconds per packet. Finally, on the bottom left side of the slide, the last factor is explored, and that is the geographical distance between ports. Especially for this project, there might be a need for remote control of a device that is located in a different city, country, or different continent. Using the average latencies from the table on the bottom right, we can generate the graph on the left that shows the effect on the throughput as the distance becomes from local to intercontinental to finally intercontinental. We can once more observe that the 4G network shows an inverse exponential curve, which in practical terms means that, especially in the up to 30 milliseconds range, every millisecond of latency will have a heavy effect on the maximum achievable performance, but on the other side, 5G has no effect, even with the added latency, no effect on the throughput, which stays at the 5 to 4.5 gigabps region, even in the intercontinental communications as well. That concludes the 5G analysis of the project, and we can now move to the performance analysis. Now that we have concluded with the development, methodology, and result analysis of the project, we can look at all domains together and evaluate the overall performance of the project. Starting again with the master domain, all objectives were met as a functional HoloLens application was developed that could trigger events and create TCP packets. The only part that was not realized was the HoloLens to server communication, something that was simulated with the use of the packet sender tool. Then on the network domain, most objectives were achieved again, and functioning as a server can successfully manage multiple user communication and transfer packets from a client all the way to the control object. Again, the only thing that was not achieved practically was the 5G implementation that was only explored theoretically. Finally, at the control domain, all objectives were achieved, as the microcontroller could successfully receive packets from the server and control the physical object. We can finally look at the project management side of the project. Looking at the planned and actual views of the second semester Gantt chart, we can observe that a few changes were made. Most of them were due to the COVID-19 pandemic, and so some tasks were affected, and so the actual working schedule had to be redesigned. The overall project, however, ran smoothly, and in the whole semester all the tasks were successfully completed. The project is now complete, and we can safely say that it pushed the AR technologies a step closer to realizing complex, real-time, and with very low latency remote control of physical objects. The main objective of this project, as stated in the project description, was the development of an AR-based remote control system using the Microsoft HoloLens. This presentation confirms that the objective was not only met, but it acts as a proof of concept that a mixed reality headset can be an effective remote control tool. The demonstration of the project will now continue.